Good morning, everybody. It's a pleasure for me, and I think also for the Institute, to have Omaira González working with us and have the opportunity to listen to the most recent work she has produced on AGNs. What can I say of Omaira? Well, she was the first person that made a thesis work on X-ray astronomy here in the Institute under the supervision of Isabel Marquez, that is sitting here, and myself. We are very proud of it because it was really a great challenge for us to enter in a new field of research. So that I think that, and she did really much better than we expected at the beginning. And so after that, she moved to United States, no, to UK, working in Leicester, that was the reference place of X-ray astronomy in Europe. She spent there 1 year or 2 years, I don't remember, 1 year. And then she moved because she's from Canary Island, you know, and so she missed in the United Kingdom, she missed the island and all these things. So she moved to an island in Greece. And she was working in Greece for a while, and she recovered her sense of humor there, and started to be happy with the astronomy that working in Crete. And well, after some time there, she went back to the Canary Island, to Tenerife, and finally she moved to Mexico, and it's not an island as far as I know, but she's happy in Mexico, and she is doing really a great work in Instituto de Radioastronomía y Astrofísica, IRIA, in Mexico, because she took the challenge to start an extragalactic group in that institute. Maybe of you know that this institute was mostly dedicated to radio astronomy, but she started with a group in extragalactic. She included her knowledge in X-ray astronomy, and she's forming an extraordinary group of people working with a multi-wavelength view of the universe. So that is her main field of research. Has been from the beginning AGNs, because we start with X-ray, so we of course study AGNs because are the more energetic object in the universe. So that we start with AGN, and she continuing with AGN, getting deeper and deeper in the knowledge of AGN. So today she's going to speak about the Toros model for AGN. So that's it's your turn.
I think you gave half of my talk already. I come here from time to time. I think at least once a year, and lately twice a year. But I'm not giving talks so many times. So let me first thanks to Isabel and Pepa for inviting me, but especially for teaching me how to do science, which is, now that I have my own students, I know it's not an easy task. So let me take this opportunity to thank them for that. In fact, this talk, which is about AGN dust at mid-infrared, is quite related with my PhD thesis. As Pepa said, I was doing my PhD thesis in X-rays, but at the beginning, I don't know if you remember, I was supposed to do the thesis on mid-infrared wavelengths. And in fact, I remember the first year, Deborah Dulcin, I don't know if you know her, most probably you know her. She's a very good friend, a Mexican astronomer, very good friend of this institute. She was coming to the institute to explain me how mid-infrared works, why it's good for AGN, to learn about the AGN dust. I was hearing her voice for minutes and even hours, and I was not able to follow any word, so I never understood anything about mid-infrared because I was so happy with her accent that I couldn't follow the words. That was really impressive. I don't know if that was the reason why I changed to the X-ray astronomy. And I don't know if that is the reason why I really decided to move to Mexico to hear this accent more often, and in particular to Deborah that I work with since I'm there. The topic of this talk is AGN dust models. I would like to explain you how to distinguish between these models. There are several of them published in the literature. This is a good example of the nice collaboration that we have been doing between Mexico and Spain. From Mexico, most of the people, I don't know if I started the extragalactic group in the area. What is certain is that I started the AGN group in area. Most of them are from there, and also Deborah, of course, Deborah Dulcin, and many people from Spain too. Some of them from here, Isabel and Pepa, and some others from the ISC. And I also have a representation from Korea with Mariela Martinez Paredes. She was actually a former postdoc of myself, and she's currently working in Korea, but still collaborating with our group. So, let's see if this works. No. This is the outline of the talk. I assume in these seminars there are students, so I decided to give a brief summary of what an AGN is, the AGN families, AGN components, the unified model, and then I will try to move fast to the topic of the talk, which is AGN dust and how to infer its properties from different point of views. I will be focusing in mid-infrared spectral fitting. I hope I will convince you that this is a good technique to infer the properties of the dust. I will explain you a couple of works that we published recently. One is based on synthetic spectra using different instrumental setups, and the other one is about using this knowledge to apply to a sample of AGN to try to infer which of these models is better reproducing the data. And I will end up with a summary. So what an AGN is, this is a bright source at the centers of the galaxies, point-like mostly, which emits enormous amounts of energy. And this energy cannot be explained by stellar processes. You need to claim something else. And this something else is an accretion disk, which is accreting material toward a supermassive black hole. Since they were discovered, many classifications have been found according to different wavelength range. I'm not showing you here not even a tiny fraction of this classification, just to have a flavor of what is going on with these families. You can classify the objects according to radio wavelengths into radio quiet and radio loud. And this is taking into account the ratio between the radio luminosity and the optical luminosity. We know now this is not a two-box classification. It's more like a continuum of ranges of radio loudness, and it's telling to us what is the importance of the jet contributing to the entire spectral energy distribution. Also, you can classify the objects at optical wavelengths, and this is something all astronomers have done it because it's where optical is where the astronomy started. And in the optical, what the people did was to classify it attending to the existence or not of broad components in the permitted lines. If these broad components exist, you classify the object as a type 1 AGN. If these components are not in the spectrum, you classify the object as a type 2 AGN. You also can classify the sources attending to the brightness of the source itself. If it's very bright, brighter than the entire galaxy, you will classify the object as a high luminous AGN, and to this category belongs quasars. If the galaxy and the nucleus are more or less of the same brightness, then you classify the objects as intermediate luminous AGN, and to that category Cephers belong. And if the nucleus is much fainter than the galaxy, then you will classify the object as a low luminosity AGN. To this category, liners belong, and I did my PhD on this class of objects. If somebody asks you what an AGN is, please do not answer, because I'm now in panels evaluating students. So please do not answer this is a bright source in X-rays, and do not answer this is a variable source. This is true, but it's not the definition of what an AGN is. AGN are bright sources in the center of the galaxies that are very well known to be the most luminous and persistent sources in the universe. And they emit in the entire wavelength range, from radio to gamma rays. And each wavelength gives information of a different component, and that's how we have found different components in these sources. These are the main constituents of this AGN. Of course, the supermassive black holes with 10 to the 5 to 10 to the 10 solar masses at the center of the system. Then you have an accretion disk, which is the one that's accreting more or less efficiently toward the supermassive black hole. These are tiny portions for the galaxies, 10 to the -3 parsecs. And then you have several regions conformed by clouds. The closest to the accretion disks are the broadline region, which is within more or less 1 parsec of distance from the supermassive black hole. And it has, because they are so close to the accretion disk, they are moving fast. And these are moving as fast as with velocities of 1,000 kilometers per second. Farther away, at distance of few kiloparsecs, you have the narrow line region. This is supposed to also be an outflowing wind that has lower velocities of hundreds of kilometers per second. And another important contribution comes from radio, where you can detect jets that can be very tiny at the center of the galaxy. It can also be very large, even larger than the entire galaxy. I've left until the end the dust, because this is the main topic of this talk. The dust is supposed to be between the broadline region and the narrow line region, so with sizes of few parsecs scale. And when already in the 70s, they realized that all these classes of AGN and all these components could be put all together into a single, more or less single scenario. This is what we call the unified model, and this is one of the latest versions of this unified model. What you have is a plethora of clouds surrounding this accretion disk. Some clouds are more or less stable, parallel to the equatorial plane of the disk. And some other clouds are supposed to be flowing material from the accretion disk in a cone-like structure. And this cone is supposed to be empty inside. And that's why, in some cases, if our viewing angle is lucky enough, we observe this object within this hollow of the cone. So we detect the lines, the clouds that are moving faster because they are closer to the accretion disk. So we will see this broadening of the emission lines in the optical, and we will classify the object as a type 1 AGN. If we are not so lucky, then we will intercept these clouds that are dusty outside, and they will block up our inner view of the mechanism, and we won't be able to see the broad emission lines. So we will classify the objects at type 1 AGN. So I hope I have convinced you that the AGN dust is important in this classification. It's important to know what is the structure, how it works, if it is the same for all the AGN or if it's changing. But if I ask you how is the AGN dust arranged, what you will say? I've been trying to playing a bit with you, giving you a subliminal message along this talk. If you didn't catch it, let me put it again. It's a torus. It's what people believed in the 70s. Even the guy who did it, put it in a plot in the 70s, is now saying that he never said that the people understood something that he was not saying at all. But the reality is that all if you go and Google, all the unification models, most of them, except the one, probably one of the few, the one I was showing you before, show this dusty structure as a torus-like geometry. But we don't know it. If you ask me what do we know about the AGN dust, I think the only thing that we can say is that it must be very little. It must be smaller than 5 or 10 parsecs, because we have never observed it. One possibility to have enough spatial resolution to actually make an image of a torus is going to submillimeter wavelengths. A lot of work has been done in the AGN field mapping the molecular torus through molecular lines. But when it comes to the dust, what you need to model, what you need to map is the continuum. But the continuum, the dust peaks at mid-infrared wavelengths, around 30 microns, and what you see in the ALMA submillimeter range of ALMA is just the tail of this emission. But this tail competes with another tail, which comes from the jet, from radio. And in a paper that we published recently this year, led by Alice Passetto, I think she came at the beginning of the year to talk about this paper. She showed that we showed in this paper that in most of the cases the jet contributes more than the torus, the dusty torus. So it's not an easy task. We have a couple of examples that we can play with, but definitely you cannot do a large collection of objects. You cannot image the torus with the submillimeter wavelengths. Another way around is doing mid-infrared interferometry. This has been done for a couple of tens of objects, and they have found nice results. For instance, they have found a non-negligible contribution of polar dust. And this goes with the idea that some of the dust comes from the outflowing wind launched by the accretion disk. But again, this cannot be done for a large collection of objects, because you need a source to be very bright in order to do this mid-infrared interferometry. So the way you can do large collections of objects is doing a spectroscopy. In this case, what we do is to compare spectra and photometry with models. And this has been done a lot by our group, comparing what is called the Clumpy Torus model by Nenkova and collaborators with data. And for that, we have a code that uses Bayesian approach to try to fit the data and to try to infer the parameters of these models using spectral fitting. But this is not the only model that is publicly available. There are at least 6. These are the 6 that I'll be talking along this talk. So let me explain you a bit about them. This is the Clumpy Torus model. There is another Clumpy Torus model, Honig and Kishimoto, 2010. There is a smooth torus by Fritz and collaborators, 2006. In 2015, these people, Steven Morgan and collaborators, proposed a model which is smooth and clumpy and can be understood as a toroidal structure or an outflow. And a year after, that, Marcos Talevsky and collaborators published a paper proposing a new model, which is again with a toroidal geometry, but now the dust is distributed smoothly and also clumpy. And the latest one is Honeck and Kishimoto 2017. In this model, what they claim is that there is a disk plus a wind, both clumpy. If you take a look to the dust distribution, some of them smooth, some of them clumpy, some of them a combination of the two. If you take a look to the geometry of this dust, most of them are assuming this toroidal that we've been assuming for decades now. But some of them also explore other geometrical distributions like winds. Also, there are differences in the dust composition, and also this has not been explored so much. And there are a lot of difference in the parameters itself, in how you construct these models and how you evaluate how is the parameter space that you evaluate for each model, and that is also important. I will show you that. If you ask me about the dichotomy between clumpy and smooth, I will say that for simplicity, the people assume smooth at the beginning, and then at some point they realize that this structure is very difficult to sustain if it's smoothly distributed. This is basically because you need your torus to be some kind of with some kind of width in order to block a good angle. So you have type 1 and type 2. In order to have this width, what you need is that the velocities are high velocities in the system, and these high velocities will produce high temperature that will actually destroy the dust itself. So it's not sustainable. So the people started to realize that maybe the dust was most likely distributed in clumps. That's why we started with the clumpy models. This is an example where some people started to show that even though the sustainability is not so well understood when you compare the shapes, and here what they are comparing is the silicate shapes at mid-infrared. What they found is that the smooth torus is explaining more objects than the clumpy torus. Another good example is made by one of my students. She's in the third year of her PhD, and what she's doing is to comparing X-rays and mid-infrared. With mid-infrared, what you have is the dust. In X-rays, what you have is the gas, but both obscure the central engine. So with both, you will have information about this obscuration. Dust and gas supposed to go together, and what she has proved here, and this is the first time it has been proved, is that you can explain with the same structure the X-ray emission and the mid-infrared emission of a single object. And the important point here is the best model among the ones that she played with is the smooth torus, not the clumpy torus. So at least for this object, the smooth torus is also doing a better job. But it's not only that we don't know if it's smooth or clumpy, the geometry, it's also that we don't know if that evolves with the duty cycle of the AGN activity. And there are some indications that it might be the case. For instance, Cristina Ramos Almeida published a couple of papers saying that type 1 and type 2 AGN do not have the same dusty structure. Type 2 AGN tend to have larger covering factors than type 1 AGN. And this means that the unified model is not the single thing to think. There is something else. There is evolution among the AGN classes. And another paper more recently is by Mariela Martinez-Paredes. She extends this kind of works to quasars, and she also finds difference when she compares with lower luminosity AGNs like Cephus. We also extend this kind of works toward the very luminosity end, to the very low luminosity end. This is something we've been doing in the group a lot. We like to work with the low luminosity agents. And what we did here is to make average spectra with Spitzer of different ranges of X-ray luminosities to see if there is evolution along the luminosity. And what we see is that, in fact, there is kind of, is what I'm trying to show you here, kind of a collapsing scenario in which you have at the highest luminosity the bigger Tori. When you move toward lower and lower luminosity, this torus is starting to collapse toward the center. There is a certain limit below which, in luminosity below which we were not able to fit the spectrum with a Clumpy torus model, so something else going on. And there is a limit below that where there is not signatures of any torus. And this is what is called the disappearance of the torus, and it's something has been claimed by theory by these people and other people, but has never been proved by the data. And this is one of the very best proofs of the disappearance of the torus at very low luminosities. So with all of this in our head, what we wanted to test is how AGN DAS model operate, how can we learn information from these models using spectral fitting? And for that, we used past, present, and future instruments. For the past, we use Spitzer. Spitzer is going to give us a wide wavelength range, which is very good to do spectral fitting. But then the spatial resolution is not so good. For that, GTC is much better. It's going to provide us 0.3, 0.4 arc seconds in resolution. This will isolate much better the AGN compared with the Galaxy. But then GTC is not so sensitive compared with Spitzer. And also, it doesn't have the wavelength range as good as it was for Spitzer. The future will be James Webb. James Webb will provide the spatial resolution and also will provide wide wavelength range, even near-infrared spectroscopy at the same time that being infrared spectroscopy. So the aim of these two papers were to try to see if we can see the difference between models, if we can differentiate among these models using these instrumental setups, also see if there are the dependence on these results with the spectral range, sensitivity, or even the host galaxy dilution that could play a role on the understanding of our sources, because AGN are always embedded inside of the galaxy, so we need to take into account that the galaxy is going to make a role. And also we wanted to see in real data if we can say which of these 6 models is better describing the data. No? For the real data, we use Spitzer, because Spitzer is what we have. It has a large collection of objects. We've been analyzing over 100 AGN. For most of the rest of the analysis, what we did is to use synthetic spectra. Let me show you the evil diagram that shows what we did with the synthetic spectra. And I'll be trying to explain this for a while. What we did is to produce synthetic spectra with several instrumental setups. The 3 that I was talking about, and also I split James Webb into 2. One considering only for mid-infrared spectroscopy, but another one considering mid-infrared and near-infrared spectroscopy with NIRSpec. Also several sensitivities, which ranges more or less of between signal-to-noise of 7 up to above 100. To see at which level of sensitivity we can estimate the parameters. We explored the 6 models I was talking about. For each of them, we produced 1,000 of synthetic spectra using these configurations, using random parameters for these 1,000 spectra. But we also check if fixed values we're going to provide a better coverage. So that's why you see some numbers next to this 1,000. And the next step was, after you produce your synthetic spectra, you fit your synthetic spectra to try to recover the initial parameters that you put. But we fit it to the same model we used to produce the synthetic spectra, but we also use the rest of the models. Because another question we want to answer is if this model can be differentiated with the others. So we can test if statistically you can distinguish this. And the rest of the diagram, not going into the details, is just to prove host galaxy dilution. And for that we included stellar contribution, interstellar medium contribution, and the combination of the two in our synthetic spectra, and then fitted again the data to try to understand what is the role of this host galaxy dilution in our estimation of the parameters. Altogether, 1.5 million fits. This goes for 3 months in up to 5 servers. I would like to acknowledge Jaime, who gave me the permission to use his own server to try to speed up processes. I also use a couple of them in Canada, and several of them in my own institute. A lot of work, but I think it was worth it because we got some nice results. Let me show you. Firstly, we wanted to see if these models can be differentiated with simple diagrams. And for that, what we did is to take the spectrum, the synthetic spectrum that we produced, and compute some slopes that define the shape of the spectrum. These are the 3 slopes I'm showing you here. I call the near-infrared, mid-infrared, and far-infrared slope just because this is closer to near-infrared, this is close to the far-infrared, and the other one in the middle of the two. What I'm showing you here is the diagram of mid-infrared versus near-infrared slopes. And this box is just put there to show the locus of most of the SCDs produced by this model, which is the smooth torus by Fritz. And each panel shows the same box, but now the SCDs are coming from the different models. So you can see there are differences between them. There are a couple of them that cannot be distinguished. For instance, the Clumpy Torus model by Honeck and Kishimoto 2010, and the Clumpy plus this wind, the disk plus wind model by Honeck and Kishimoto 2017 cannot be distinguished. The same happened between the smooth torus by Fritz and the smooth plus Clumpy torus by Stalewski and collaborators 2016. The explanation is that these models are sharing, well, in this case, even the radiative transfer code, but they mostly share the parameter space and the geometry somehow. And this also happens for this one. These are not using the same radiative transfer code, but they definitely share the same geometry. These are people that are closely working together, and so they decided to use exactly the same geometry in this second model. But in some cases, you can distinguish between them. The second diagram is the far infrared versus mid infrared. In this case, again, these models are pretty similar. These are not so similar, as you can see, but still they share a lot of a big portion of the locus. In this case, what we believe is happening is that in this case, also they use the same geometry and parameters. They do not produce SCDs for the same wavelength parameter space range. That's why this is narrow parameter space range than this one, so this is producing larger values for this slope than in this case. But definitely you can distinguish among them using these diagrams. For instance, definitely you can distinguish between these two and the rest because they normally produce higher far infrared slope than the rest of the models. Another way to see this is using the spectral fitting. You have your synthetic spectrum, you fit it to all the models, and what you are seeing here is the chi-square distribution of these 1,000 synthetic spectra fitted with all the models. Let me explain. This diagram, for instance, these histograms, what I'm showing you is that in the case that you produce synthetic spectra with a Clumpy Toros model by Nenkova and collaborators, you fit it to all the models, and the only one giving good results, and notice that this is a log scale, so this is very, very bad. The only one close to one, which is telling to you that this is the right model, is the one that we use to produce synthetic spectra. This is telling to us that this model can be distinguished based on chi-square. Just do a chi-square and you will know if this is the right model or not. But this is not the case for all of them. There are a couple of examples. In general, it works, but there are a couple of examples that is not working so properly. One is the comparison between the Clumpy Toros model by Honeck and Kishimoto and the Clumpy disk plus wind model by Honeck and Kishimoto 17. In the case of if you produce Clumpy disk wind model with synthetic spectra produced with this model, and then you try to fit it all of them, it won't get good results except for the case of Honeck and Kishimoto 2010. And the opposite is also true. It's telling to you that these two models cannot be distinguished based on chi-square statistics, but it can definitely be distinguished from the others. Similarly, similar things happened with smooth Toros model by Fritz and the smooth plus Clumpy Toros, smooth plus Clumpy Toros model by Stalewski. In this case, if you produce synthetic spectra with this model, you can reproduce most of them with the smooth Toros model by Fritz. The opposite is not so true. You can produce, if you produce smooth Toros model, synthetic spectra using the smooth Toros model by Fritz, then you partially fit some of them, but not all of them. Again, this is due to the parameter space, which is not the same. Also, the geometry and the parameters are the same. But what happened with real data? Then we go back to the real data, these 100 Spitzer spectra that we were analyzing, and we produced the same quantities that we use for these diagrams. And these are the stars. The stars are the data. These circles are the models. And what you are seeing here is that in these diagrams, the best one, the best models reproducing the data are these two, the Clumpy Toros model by Honeck and Kishimoto 2010, and also the Clumpy disk plus wind model by Honeck and Kishimoto 2017. But look what happened to the other diagram. Now, this is clearly over-predicting far infrared slopes. They are not good at reproducing the data, and what is reproducing the data the best is this smooth Toros by Fritz and this smooth plus Clumpy Toros by Stalewski. Another thing I want to give your attention is that there is a lot of SEDs that do not reproduce any data. And this happened for this diagram, this happened for the other diagram. No? This is telling to us that perhaps models could start to think on redefining the parameter space, and that will help on the matching between data and models. We also studied the estimates of the parameters. We wanted to know how good we will be with the future James Webb to estimate the parameters of these models. And this is what I'm trying to show you here. Each panel gives you, well, what we compute is the average error compared with the parameter space for each parameter and each model. Each panel is each model. And each quarter of the panel shows one of these instrumental setups, each angle a different parameter. And each color a different signal to noise ratio. So what you are seeing here is that in most of the cases, except this one, which is horrible, the rest of the models can be restricted to up to a certain level. With, around 15% of the parameter space can be restricted for most of the parameters as long as the source is bright enough. But in this case, it's impossible, and the answer is very simple. This is the model that has, because it's a disk plus a wind, it has the larger number of parameters involved. It's 8 parameters compared with 5 or 6 for the rest. So it's quite difficult to restrict just with using spectral fitting. For this, you will need another technique or add additional information. We also check if stellar dilution, a host galaxy dilution was playing a role. What is the problem when you start having a galaxy in the middle of your AGN and yourself? And these are the results of including stellar dilution, not going into the details, interstellar median dilution, and also the combination of the two. The main answer, well, apart from this model is still not restricting anything, is that you can still do the job as long as the AGN is dominated at least 50% of the mid-infrared emission. But what happens to the data? Because I was telling to you that the Spitzer spectra are not very good with the spatial resolution, so galaxy is going to be an issue. What we did is to fit the real data with this model, with this AGN dust model that are proposed, but also including these the other contributions, stellar, interstellar median, and the combination of the two. And this is the plot that shows the main result. First of all, if you make the percentage of objects which are AGN dominated according to each of the models, this is the gray bars that I'm showing you here. Even this number, which gives you the idea of how much is the AGN contributing to the mid-infrared spectrum, this number depends on the model. So it can go up to 55%, 75% for the smooth model, but it can go down to 50% for some other models. Another important message from this plot is that if you use just your AGN dust model and you try to fit your Spitzer spectra in the entire sample, what you get is the black bars that I'm showing you here. So the largest portion of objects that you can fit using just the AGN dust model is around 25 and can go up down to 0 for some of the models. When you start to get better results is when you start to add host galaxy dilution, which is telling to us that the Spitzer spectrum in most of the cases they need these stellar host galaxy components in order to fit the data. You can go up to around 45% in the case of this disk plus wind model, and the other one that is doing a roughly good work is the Clumpy Toros model by Nenkova, up to 30% of the sample. Another nice result comes when you try to put your objects in boxes. And we did in two ways. First of all, in AGN classes, type 1, type 2, to see what happened. And also in X-ray luminosities to see if there is any trend with the volumetric luminosity of the system. We know X-rays is going to give us a good indicator of the volumetric luminosity of the system. And what we found is something interesting. This disk plus wind model seems to work very well for bright sources or type 1 AGN. Then when you go to a lower luminosities, the Clumpy Toros model is as good as the other. So it seems that there is some kind of an evolution in the sense that the bright sources prefer this wind, which is completely normal because the power of these bright sources is enough to launch a wind. While in the case of lower luminosities, it seems that the dust is arranging more a Clumpy Torus distribution as we thought at the beginning. We also did a lot of work on the parameters that we obtained from the real data. In order to do that, what we did is producing posterior distribution for each of the parameters. This is an example of one model, one single object. I'm not going to go into the details, just to give you an overview of what we found from the real data. We confirm with real data that the parameters can be roughly restricted to the 15% of the parameter space for all by this Honig and Kishimoto 2017. This is the same that we obtained with the synthetic spectra. The resulting parameters depend on the model used, even for the viewing angle. And this is very important because we wanted to know what is the viewing angle and if that matches with the classification that we have in the optical. But even that number depends on the model that you use. You need to be very certain that the model that you are using is the best description of the data in order to determine the parameters. And many objects tend to show upper or lower limits of the parameters. This again is saying that maybe models should rethink on the parameter space, because this could help on finding a better match for the data. And the most robust quantity is the total mass, which is consistent with the same consistent with the same value irrespective of the model. For the rest of the parameter or derived quantities, it depends on the model. And the last point is that the outer radius of the dust structure inferred from the smooth model is twice smaller than that inferred from the clumpy model. And this is very funny, because this is something that was taken as a disadvantage of the smooth torus model, because at the beginning they were producing very large tori, and so this large tori will be large enough to be seen with, I don't know, HST. Nobody has seen it, so the people believe that these smooth torus models are not feasible because of this large torus obtained. But what is true is the opposite. When you pick the same sample of 100 of AGN, as I did, and you feed them to the smooth and the clumpy torus model, you always get a larger torus for the clumpy distribution when compared with the smooth distribution. And this is something, in fact, reasonable, because this clumpy, in order to fill up with the same amount of dust, you require a smaller radius in the smooth distribution than in the clumpy distribution, because you have empty spaces. I'm almost finishing. Just to tell you that there is a lot of room for improvement. These are the residuals of the data when you compare with the 6 models. And you can see that there is a lot of dispersion in the residuals, which is telling us that the models are not so good describing the real data. There are more complexity. You can think that this is because of the host galaxy dilution. But when you go to the very good spatial resolution obtained with ground-based data, this is something that we can do only for this object, because this NGC 1068, which is a very famous AGN, is the only one that has been observed in the Q band. For the rest of the object, what we have is only N band. In this case, this is something that a student of mine is doing. This is Cesar Victoria Ceballos. He's trying to fit with this set of models, and he, as you can see, he gets very bad spectral fitting. Is not able to fit N band and Q band at the same time for this single object. In fact, what he has to do to make the trick is to allow variations in the parameters between N and Q band. This is telling us that the dust is more complex than the models. We wanted to see, well, he's playing with the new SEDs obtained with radio drift transfer code to try to explain both bands at the same time. But what we want to see if this is just one case, because NGC 1068 is a different one, or this is the general rule. For that, we need more Q-band data. We apply for it in GTC. We obtain the data. They're supposed to be observing right now. Let's see. I don't know if the instrument is even in the telescope. But if we have more data, we can tell if this is a general rule, and indeed dust in AGN is much more complex than we thought. Just a couple of advertisements. Of course, the future of this kind of research is James Webb, and involved in several actions. One of them is a James Webb masterclass in Mexico that I'm organizing, among others, and it's going to be in February 2020. It's going to be broadcasted, so if you are willing to attend, just let me know. I can organize that. Another one is the Reunión Extragaláctica in Mexico, REM, which is organized every 3 years. This is the second one. I'm also organizing it, and it gathers extragalactic astronomers in all the countries. So if you are an extragalactic astronomer and you want to meet most of the people in Mexico in the field, so it's a good opportunity, let me know. Let me finish just with my group. I'm very proud of it. It started with myself and myself alone 5 years ago. Now we are 9 people, including Mariela. Most of them master and PhD students. We are always looking for new young researchers. So if you like the topic and want to join our AGN team, please let me know. And well, this is just the end with my summary. I'm not gonna read it, but I will take any question if you have it. Thank you.
Thank you, Omaira, for this very nice talk. Now we have time for a few questions or suggestions or comments.
Have you tried to consider the Eddington radio in the analysis, which is the effect, and if there are kind of difference between the different kind of AGNs? Because Eddington radio is modifying basically the accretion disk structure, the density of the BLR, ionization parameter, and also radiation pressure is really important. So if the dose is affecting also the BLR and accretion rate is affecting Toros. So.
And I totally agree with you. The two key parameters to compare anything in an AGN, or at least to have in mind, are the black hole mass and the accretion rate. These are the two main numbers that you have to have in mind, because the same accretion rate with a low mass is not the same than a high accretion rate with a high mass. No, it's not. These are the two parameters. The problem here is to take black hole masses. This is a sample of 100 AGN. Black hole masses are estimated. The best one is reverberation mapping, but this goes for a very few, mostly CIFE ones. So you will estimate very well with CIFE ones, but you won't have any measure for the others. The others are indirect measurements. So my experience is that even using reverberation mapping, when you go to the literature, you find several measurements for a single object that do not agree between each other. So you end up not knowing what you are doing. I made a compilation of some of them, tried to see if I was able to find a reasonable amount of them, but I remember it was like 20% of my sample, so nothing important to make a plot and to see the effect, but definitely it will be an important number to have.
More questions or comments?
Thank you, Omaira. Really great talk and great work. So here for the beamed AGN, you consider though with jet independently on. So beamed here are just the AGN with jet.
There's a classification coming from Veron, I would say. So it's like a jet that is pointed toward you, like a Belle-Lac or something like that. But they are very few. I'm not commenting on them because they're kind of aid sources. So statistically it's not relevant.
Yeah, that's actually my next question. Like how do you, what is the sample that you have for each of Seifert 1, 2, those that are, and if the sample is not, if you don't have the same number of sources, then do you take any kind of parameter into the case, like any kind of weight? And the third is related with low luminosity AGN. So basically, here you have the luminosity below 43. So do you consider the right plot applied for liners and low luminosity AGN in general?
This is not a very low luminosity. This is just a trend between a narrow range. This was set to have more or less the same object in each bin, so we can compare. This happens also for Cephus. Your question about the number of objects in each box is more or less the same, but definitely we don't have objects with a very low luminosity because of the way we constructed the sample. When it comes to low luminosity, my feeling is that you always have to pay a lot of attention. So you need to do a very careful job to select them. Then it's going to be very low sensitivity. The host galaxy is going to contribute a lot. So you have to be very careful with them. So it's better to analyze them closely in a different analysis, no? And then you can compare with this, but they need a much more detailed analysis.
Thank you very much for such a nice talk, Omaira, and congratulations for such a success with your group. My question is more a comment, is related to the fact that normally people just take one model to compare the data with, and it has been the case many, many times for the NCOBA, for instance. So have you an idea of what main conclusions circulating among the community could be somewhat wrong because of incorrect use of such models? Or have you have any contact coming from people interested in knowing what model is the best to use in each case?
For instance, well, I work a lot with Cristina. She's not currently working on the topic, but she was working for a while in a Clumpy Toros model, spectral fitting using Bayesian approaches. I was showing you some these ones. But even if you talk to her, she will tell she's not confident on the parameters itself. What she is confident on is to the comparison using the same model between types. No? If she finds, for instance, that the covering factor is higher in type 2 than in type 1, she's using the same model to compare with, and she's confident that if she will use another model, she will get the same result. I don't know of my future plans to use ground-based photometric and spectroscopic data to isolate very well the galaxy. This is the advantage of this kind of works. They have been using ground-based data, and I plan to compare with several models to see if that's the case. I hope so, because it looks like some reasonable result.
Okay. Thank you. So, yes, another question is related with the plots where you compare mid-infrared, near-infrared, and then far-infrared, mid-infrared. So there is, in all 6 models, it's after these ones and then the next ones, no? So basically in all models you have, actually when you compare with the real data, if you can go to the... models, but this, with all models you have, but especially the second, third, and then fourth, and the last one, the 6th, you have a huge range of parameter space that is not covered with real data, no? So yes, so even in the one that Hoyning from 2017, that at the end you take as the best one, and then for Nenkova as well, you have this big space in both parameters that is not covered with real data, no? So basically we don't know what is happening there. We don't know if the real data are not covering because of the limitation in our observations, or because these models do not work well for this range of parameters, no? So like if you take the first and the Fritz and then Stalewski model, I mean, you do get much better fitting in this case, no, for mid-infrared, near-infrared. I think for the far-infrared, it's a bit different, you know. So even so, at the end, you do take the last model and then an Nenkova model as the best ones, no. So this is a bit a contradiction for me, no, that, yeah.
What I was telling to you is that if you use just the AGN dust model, and this is the comparison I'm showing you here, data and just the pure AGN dust model, then you need something, you are not able to explain the data because these are producing much higher far infrared slopes. What is making the trick is that you include other contributors. In this case, what is making mostly the trick is, well, in this case, is interstellar medium contribution. And you can see this, I didn't have time, because I fill up these models, this data, with the combination used to fit the best combination used to fit the spectrum. And as you can see, most of them need this I, which means interstellar medium contribution. This makes the trick because then move the SCD to higher values, which, to lower values, which is what is needed by the data. So if you use just the AGN dust model, you won't be able to fit it because of this mismatch. But then when you include the host galaxy devolution, then it seems that it's working. If this interstellar medium contribution is true or not is difficult to tell because the interstellar medium contribution peaks even at higher wavelengths, around 40 or 50 microns. We will need that points in order to see if indeed there is a contribution of interstellar medium. But if you go to that wavelength, the spatial resolution is terrible. So at the end you will not know if that is because the spatial resolution is worse or if because the interstellar medium is needed. So it's a very tricky situation. What we need is to isolate the nucleus and then compare with the pure models. That's why.
Because if that's the case, I missed that point during that. But if that's the case, then it's even more tricky because if you're applying the interstellar medium contribution for the host galaxy, but then you take one general case and you don't take into account the morphology, for example, of the host galaxy and how it can also affect the
amount of stars that you have there. Inside of your beam is impossible to take into account in any other way, as far as I know.
Questions? Comments? I have one myself that is about the composition of the dust, because you saw in one of the last figures the residuals you have, and in particular with the silicato, because the silicato is at 10 microns. This line, some is in cipher 1 in emission, in Compton thick is in absorption, and so this make the. And don't you think that that there is something missing in the models due to the dust composition?
Yeah. And this is the thing that nobody has explored. Very few attempts, and they don't publish the SCDs that they recovered. Just they publish one single composition of the dust with not only the composition, the sizes of the dust. I was hearing a couple of years ago a talk of a physician who was playing with dust, nanoparticles, and he just hitting the dust changed the shape of the dust and changed the extinction. So I was discovering that I was doing just toy models, knowing nothing about the dust, and the dust can do a lot on the results. In particular about these silicate futures, which are around here and around here. This is probably mostly associated with the dust composition. I'm working with Mariela Martinez Paredes in trying to focus on these silicate futures and trying to focus with the different models, but focusing on the composition that they are using for each of them to try to see if we can tell which is the best. But they definitely work with only the galactic one and very few, no? But yeah, definitely.
If there is no more question or comment, thank you, Omaira, for this nice talk. And see you soon. In case, and tomorrow morning, she's leaving for Calar Alto tomorrow afternoon, so in case she's working in my office, so in case of any of you want to ask question, to discuss longer with her, she will be there. Okay?